The next lecture is about edge detection, and we will see how we are going to make use of all the filtering operations we have studied in the last lecture. Let me quickly go over the outline, what all we are going to cover in this lecture. First of all, we'll try to understand what exactly is edge detection and some motivation why we need to perform edge detection. Then we will look into some of the challenges which we face, and the most important is noise. What will happen if there is noise present in the image, how that will affect like your edge detection algorithms or your schemes you're using. And then we will go over a few algorithms which are used to perform edge detection. And some of these are very old algorithms, like decades old, but we will see like still they are being used today and how they are very effective. So these are Privet, then Sobel, Marhilrith, and then finally Canny edge detection. Okay, so let's start with the basics of edge detection. Now, we were talking about image derivatives, and we saw that if we use image derivatives on like any image patch, it was giving us a sense of how the values are changing, how the pixel values are changing in that image. Okay, so that's the sole idea of detecting edges. So if you have sudden changes in your image, if the pixel values is changing, then you consider that as an edge. And if the value is not changing, it's smooth, then you don't have any edge. And if you think about like how you visualize your images, that's exactly what happens near the edges in your images. When you have some shape or some objects, the value of the color, or you can say the pixel value, actually changes. And why this is important, this will give you like some kind of semantic or shape information. For example, if you perform edge detection in an image, it will just give you the boundary of that object, right? And another interesting way to look into this is if you have an image, it will have a lot of pixels. And if you have to store that image, for each pixel, you will have to store, if it's a RGB colored image, we'll have to store 3 values, right? And that might be too expensive, like in terms of the amount of memory it will require. But instead, if we just compute edges in that image, which also gives us a sense of like what object is present, because it is giving you the shape information or the boundary information, right? In that case, you only have to save like where edge is present and where edge is not present, which is like very, very less expensive in comparison to storing all the pixel values. All right, so let me give you a very simple example of edge detection, what it looks like. This is again the standard image which we have been using. So this is the input grayscale image, and after performing edge detection, we will have something like this. And here you can see that all these lines, or you can say like all the pixel values which are highly active or which have higher value, are the edges. So they are representing edges present in this image. And by just looking at this image, you can make a sense of like, okay, this looks like a girl, there is a hat, and maybe some background objects of this boundary. So you still preserve some semantic information there. Of course, you are losing a lot of texture and all that because you don't have like pixel level information preserved here. Okay, so that's how like it will look like after you perform edge detection. And you can see that at the boundary of the cap, like the pixel values must be changing because you are seeing like different gray levels here, right? And that is causing this edge to be formed here. So you can see like you can clearly define this seems like a cap to you just by looking at the edges. Okay. Now, so that was one example. Now, why we observe edges in images? Let's try to understand that. What are the different factors which are actually responsible to form these edges? So the first kind of edges could be like the surface normal might be changing, right? For example, if you look at this location, so if you look at just the surface, then the surface normal is actually coming towards you, right? At this location, it's coming towards you. So it's like in some kind of horizontal plane. So if you draw normal, it's coming outside. But suddenly, if you move to the top of this cap, the surface normal is actually pointing upwards. Right, so at this location, you can see that the surface normal is actually changing. It's going from like in the horizontal direction to the vertical direction. And whenever you will see that the surface normal is changing, we'll observe some kind of edges there. And that's why we have this edge. Okay. The other reason could be you have discontinuity in depth. And if you look at this location, so this pixel value belongs to this bottle, and on the right, that's kind of a background. So if there is a background and there is an object, then of course there will be difference in the depth. So whenever there is a difference in the depth, you will observe some edges. Okay. Now that's not like the only reason you will have edges. It could be like there is no difference in the depth, but still you might observe some edges. So that is the example, and this is like the change in the surface color. So the depth is not changing, the depth is same, but you can see like, because like the text over here, which is written on this bottle, the pixel values or the colors are actually changing, right? And that letter there is causing actually this edge. So it doesn't always have to be depth. And also, like if you look at this, the surface normal is also not changing. And like again, there are a lot of other factors. Another factor which you can discuss is the illumination discontinuity. For example, if you look at this location here, if this bottle is placed on a table, right? So if you look at this table, I mean, it's still the table, and which means the depth will not change, the surface normal will not change, and of course, like the surface color is not going to change because the color might be uniform on the tabletop, right? It's just there's a shadow coming from this bottle, which is causing this edge over here. So this is coming from the discontinuity in the illumination. Okay, so there are a lot of different factors which are causing these edges. Now let's try to understand how we can model these edges. There are again three different ways we'll try to cover. So the first type of edge is step edge. Okay, so step edge is like you will have like some continuous value in the pixel color, and it suddenly changes. It changes to like some other value, and again it remains the same. So this is kind of if you recall from the previous lecture, like we were talking about uniform distribution, where we had the step function. So this looks exactly like a step function, and this is called a step edge. Some other edges could be not, they might not be this sharp. There might be some continuity there, and these are called ramp edges. And what's happening here is when we are changing levels between these colors, so again, you're going from this level to this level, right? Which is exactly the same as this scenario here. The only difference is you are not doing that abruptly as a step. You are doing that like in some continuous fashion. So it's increasing gradually. Okay, so this is called ramp edge. The other kind of edge is like roof edge, and this is slightly different from these two edges. In this case, like your pixel value is low, it's increasing, and then again, it's coming back to the original value. So it's increasing and coming down. So it's kind of forming a roof, and that is causing this edge. Okay, so these are three different models. Now, one of the question like which we should try to answer is, okay, all right, that's fine. Those are edges. The reasons we understood why they are forming. We try to understand different models, but why extracting these edges is important. We try to cover that briefly when we talk about it can reduce the memory consumption to save your images, but still preserve some information. But that was just one use. There are a lot of other different applications where edge detection can be useful. So you can use like maybe object recognition as a downstream task. So you can extract edges from the images and use that for recognition, right? You can use it for like recovering some kind of geometry. So for example, like if you have an image and there is some occlusion, right? So if you just try to extrapolate edges, or you have some kind of prior knowledge, so you can try to recover those objects. So that could be one interesting application. And the reason is like, again, so these images are just showing you edges over here. I mean, you don't have any pixel values. You don't know what color we have, what kind of texture we have. It's just like edges, right? And still, as a human, we can say that this is a plane, this is a house, and this is maybe a mouth, tongue sticking out, and nose and an eye. Okay, so which means that edges are powerful and they can be used for like a lot of different applications in computer vision without even using like the color values. Okay, so now we talked about that motivation, which is good. Now let's have a very close look at the actual images and what does like having an edge really means. So this is an original input RGB image, and this is let's focus on this particular patch over here. So if we zoom in on this, it will look something like this, and you can see here that there are like multiple edges, and these are vertical edges, right? This is the first actually. This is not even visible here, but this is an edge, and I think this is the surface normal is actually changing. And again, we have an edge here. This could be like illumination due to different lighting conditions. And again, this is different lighting condition, or the surface normal might be changing. It might be like both might be happening at the same time. Okay, so we have all these edges here. Now, again, we have an edge over here. This is again, the surface normal is changing, but again, the lighting condition is also different, which is causing like the pixel values to change. And this is like interesting. The surface normal is not changing at all. The illumination is also not changing. It's uniform. It's because of the texture which is there at this location, right? So that's why we have all these edges. Now, as we discussed earlier, like edge is something where the image intensity or the image pixel value is changing. Okay. So, and again, this is like an example of roof edge, which we discussed earlier. The pixel value is changing, then again, it's coming down. Now, if you try to slice a single row from this image patch and try to plot that as a one-dimensional function. So we talked about like the intensity profiling, right? So let's say we draw intensity profile of this with this row. So it will look something like this, because starting from the left, it's all white, very high. It's kind of bright pixel, so the values will be high. And suddenly you can see that there's an edge and it's becoming darker. So it will go down and then it stays the same. This corresponds to the center location here. And again, it will rise and it stays the same as the initial level. Okay, so if you draw this intensity profile of this particular row from this patch, it will look something like this. Now, by just looking at this, you can say that, okay, I mean, we have a sense of where the edges are present. We can say that, okay, I mean, the pixel values are changing here, so definitely there is an edge. And we can say that pixel values are changing, there is an edge. Okay, so let's try to see like how we can extract these edges automatically. Considering this as a one-dimensional function, if you compute first order derivative of this function, you will get something like this. I will walk you through like how we get this plot. Starting from the left, so first just a quick recap. Let's walk through like how we can get first order derivative of this function, which is coming from this image patch. And just a quick recap, derivative is just computing whether the function value is changing or not. Okay, so that's exactly what first order derivative was. So if we start from the left and we start moving right, so for each consecutive locations, we will compute whether the value is changing or not. So we can see value is not changing. So the derivative is 0, right? So this is the 0 level, and it will remain 0 until we reach this point. Okay, so this is 0. And as we move forward, we can see the value is actually going down. So if you compute the difference, it's going to be a negative value. And as you keep moving, you can see that the slope is actually increasing. And you also know that from your high school maths, derivative kinds of also reflects what is the slope of your function at any given point. Okay, so if you know that, then you know that the slope was actually 0 when we started, and the slope is actually increasing. And if the slope is increasing, it's going in the negative direction, which is fine. That's why we are going in the negative direction. And at this location, when we reach here, it's kind of the maximum slope which we are observing. And this location is exactly at this point. When if you will draw like the tangent to this curve, tangent again gives you the slope. So this tangent, the value will be maximum, the absolute value. All right. And again, as we move forward, the slope of that tangent will again gradually start decreasing like this. and it will be exactly the replica of what we observed before this point. And again, the slope was like this. It was increasing, it became maximum, and then it again coming back. All right. So that's the maximum. Again, it's coming back. So it will again come to 0. And this point is at this location when again the values are not changing at all. So the derivative stays 0. Okay. And again, you can repeat the same process for this curve. And again, this is actually increasing. So your slope is positive. And that's why you get the same kind of bump, but it's in the positive direction. Okay, so that's how you compute first order derivative of this simple intensity profiling. And if you look at this, by looking at this curve, we knew that, okay, this is an edge and this is an edge, but we didn't know like how to automatically compute that. But after computing first order derivative, looking at this, you can easily automate this. You can say that, okay, whenever there is a dip or whenever like we see like a hill, that's an edge, and which is actually true. So this edge over here belongs to this vertical edge, and this edge over here belongs to this vertical edge. Okay, so which means that first order derivative actually helps you in computing edges in your images. So these two peaks are kind of indicating where the edges are. So far so good. But let's see like what's the issue with this simple process, because if this is it, then we don't have to do anything, right? It's a very, very simple process, but that's actually not true. Now, let's try to closely study like the intensity profile of this image. And as we go from left to right, this is the intensity profile. It kind of remains the same. It goes down. And at this point, you can see it's going down because we have kind of a dark background here, right? So it goes down and again, it comes up. So this is kind of a more realistic intensity profile from a real world image. And you can see that it's not very smooth. There are a lot of like jerks here, a lot of ups and downs. But still, we can see that whenever the intensity is changing, we do see these dips. And these are kind of indication where the edges are present. So let's compute derivative of this intensity profile. I won't go through like all of this, but you can like do yourself and you know like how to get these peaks, right? So this is the first one you can see here. And again, so all these peaks, they are kind of representing whenever there was a sudden change in the intensity values. And if you look at the intensity derivative, and if you look back at this image, so each of these peak is actually corresponding to the edges present at these locations. Okay, so far so good. Now let's try to add a little bit of noise like in your images, in your image. And usually we know that images are actually noisy. So let's add like a little bit of Gaussian noise and see what happens. Now, what will happen is if you have noise, you know that it comes from like a probability. For example, if it's a Gaussian noise, so each pixel will have some value added, right? Or maybe subtracted. And if you, let's say, add Gaussian noise on this image, then the intensity profile is going to look like this. And no, so this is the intensity derivative. And here you can see that, okay, the edges which you were observing earlier, they are kind of gone. Right? So you are seeing like a lot of peaks here. All of these are peaks. Of course, you have like higher peaks, which is fine, but you do have like shorter peaks as well. So now the question is, if we observe that many peaks, mean, of course, those are not edges, right? Those peaks are there because of noise, because due to noise, like your pixel values are actually changing in the local neighborhood. And that's why it's hindering you from computing the actual edges. Okay. So this is a simple function. Again, consider this as like intensity profile coming from an image. And you can see like there's a lot of fluctuation in the signal, which is again coming from noise. Okay. Now, if you compute a derivative, as I showed you earlier from a real example, even for this function, this is what like a first order derivative will look like. And at each location, since the pixel values actually intensity is changing, you will get a lot of peaks. Whenever it's changing, you will get a peak. And with this kind of signal, you can't say where the edge is present. So let's try to see what can be like a simple solution to resolve this. Okay, so all this is fine. We talked about that. We can actually smooth a signal using some kind of filtering. Okay, and smoothing, we have seen like box filter, we have seen Gaussian filter. All those filters help you in smoothing your signal. And when you smooth your signal, what it does is it tries to utilize the neighborhood values and then use the average and replace the value of the current pixel, right, in your image. And it will do the same for the signals as well. So if you smooth, let's say in this case, we are using a Gaussian filter. A Gaussian filter will look something like this, which means that you are paying more attention to the current pixel, slightly less attention to the neighboring pixels, but you're still looking at the neighborhood. So it will have some kind of smoothing effect. And if you perform filtering using this Gaussian kernel of this function, then this is the filtering operation. And you can see that the signal becomes something like this. So all the noise is actually gone. So filtering using Gaussian is helping you in getting rid of the noise which was there. And then what you can do is you can just compute derivative of this filtered signal. Right. So if you compute derivative, it will give you something like this. And this bump over here actually corresponds to this change in signal intensity, which represents an edge. Okay, so smoothing is like one operation which helps you to address noise and still be able to compute edges in your signal or in your images. Now, there is like some optimization which you can perform here, and we'll talk about optimization a lot when we talk about filtering or edge detection later on. So if you look at this operation, right? So this is a filtering, or you can say correlation operation, right? And you're computing derivative of this function, and we have seen that if you compute derivative, it's kind of you can compute derivative of the filter itself, right? And then apply that to the filter. So this was the original filtering operation, and you're computing the derivative, right? So you can bring out like the function itself and just find the derivative of your kernel. Okay, because convolution is differentiable. We I think saw that in one of the properties in the last lecture. Now, why this is important? Because your function or your signal or your image, that is going to change, but you beforehand know what your filter is going to be. And if you know that, you can compute the derivative beforehand. Okay, you don't have to wait for the signal itself. So for example, if our if a filter was Gaussian, then what we can do is we can just compute the derivative of the Gaussian, and that derivative is not going to change at all. And what we can do is then use that derivative of Gaussian to actually perform filtering. All right. So if you compute derivative of your Gaussian, you will get something like this. And I can go over this quickly, but I don't think there's a lot to understand here. So your Gaussian will look something like this, right? So when you're computing the derivative, again, you can see that your signal value is actually increasing. Again, we can just follow the slope. Initially, the slope is 0, and it's gradually increasing. And the slope will be maximum when you are at this location. Right, so that corresponds to this value. But again, the slope is going to come down. And as you reach the top, the peak over here, again, your slope is 0, which corresponds to this location. And again, you can repeat the same thing for the other half of the Gaussian, but again, it's in the different direction. So you get like a peak towards the negative direction, right? So that's the differentiation of a Gaussian function. And now what you can do is use this kernel to perform filtering, and the result is not going to change. You will get exactly what you got using like these 3 steps. Okay, so you're saving like 1 step here. So that's kind of optimization. All right, so we discussed like smoothing helps, but again, it's really important to understand. We also saw that in the last lecture, it actually depends what kind of filter you're using and like what's the size of your filter, and that will completely change the kind of output you're getting. So you can just have like you can just use 1 pixel, which means you're not changing anything. You can use, let's say, smoothing over 3 pixels. It could be a 3x3 kernel. Then you will see that the edges are actually also getting blurred. And if you keep increasing the size of the kernel, it's going to be even blurring. Okay, so which means that if you do too much smoothing, I mean, of course, it will remove the noise, but again, you're losing on some of the edges as well. So if you will have like very soft edges, all those edges might be gone just using smoothing. So if you want to recover those edges, then smoothing might not be a good idea. Okay. Now let's quickly go through how an edge detection algorithm can be evaluated, because we want to automate this. So far we are just talking about by just visual inspection. Okay, this edge detection seems good, this is not good, but we should have like a computational way or like a quantitative metric to compute how good our edges are. So we'll briefly talk about that. And this again, you might, if you have taken machine learning course or any statistics course, you might know like what recall is, what precision is. So we'll quickly go over this. Now, let's say this circle over here represents all the edges, which your method is actually saying are edges. All right, so this is kind of results from your method. The red one is, let's say, the ground truth. So this is the set of actual edges. So if you will quickly look at this, you can see that you are saying all these are edges. But again, this is at a conceptual level, I mean, we don't have any edges here, right? So this is just like the set of edges we have. So this is the area where we are saying there are edges, but they were actually not ground truth. And the central one is like the edges, which were actually edges. And our method also said like it's edges. And these are all the edges, which were actually edges, but our method actually was not able to recognize these as edges. Okay, so we have terms for all these. The center one we call true positive because our method said it's an edge and it was actually an edge. Okay, so that's true positive. Then true negative, all these were not edges. These are like outside your red circle, right? And our method also said these are not edges. So these are negatives, but true negatives. Then the next one is false positive. So false positive, this region where our method said these are edges, but these were not actually edges because these are like outside the red circle, right? So we call them false positive because our method is saying these are positive, but actually these are not positive. So false positive, okay? And last one is false negative, which again, it's the same scenario as false positive. So our method said these are negative because we don't recognize these are edges, but these were actually edges because these are inside the red circle. So we call these false negatives. So once you understand like all these terms, you can easily compute precision and recall. And these are the formula. I will just give you the intuition. We'll not go over the equation. You might know already know this. So precision is how correct your method is. All right. So if your method is saying something is an edge, so is that correct or not? So that tells you about precision. All right. And that's exactly what is being shown here. True positive over the results of method. Right. So for example, your method said 100 of these were edges. Right. So that's the result. But actually only 50 of them were edges. So that will be true positive. So then your precision will be 0.5, or you can say 50%. Okay. So it's about like what your method is saying and how much of that is correct. That's precision. Recall is slightly different. Recall tells you if there were, let's say, 1,000 edges, then out of those 1,000 edges, how many of edges your method was able to detect, right? So it's, you can see like it's kind of recalling what is an edge and what is not an edge. So if you look at this formula over here, it says true positive over ground truth. All right. So let's say the ground truth, you had 1,000 edges. All right. And true positive, your method only could detect 50 edges which were correct, which means that out of 1,000, your method only predicted 50 edges. So the recall will be 50 over 1,000, just 5%. Okay, so that's like the slight difference between precision and recall. So precision is how accurate your method is, kind of, and recall is like how much of it the method can actually recall or collect. All right. So you compute like precision and recall, and then you create a plot which is called like precision recall over precision. I will show that plot later, which is actually useful to compare different algorithms. Now, a good edge detection algorithm will actually find all the real edges, all right, and it will try to ignore noise and other artifacts. And not only that, it should also try to localize it well. So what I mean by that, for example, this is a true edge, and your method is giving something like this. So it's not like localizing it well, although it's detecting edges, but it's not localized, right? Again, this is like slightly better, but again, the locations are not correct. And in this case, you can see like this bar over here, if this is representing the red one, then it's actually giving you the correct edge, but it's kind of too many responses, right? So it's over predicting. Now, looking back at precision and recall, in this case, you might get a good precision because it could be like 3 of these are correct and 2 are incorrect. So the precision will be 3/5. In this case, let's say this is the correct edge. So in this case, the precision is actually better than this. The precision will be 2/4 because these 2 are correct and the total are 4, which the method predicted, right? And again, you can compute recall as well. So if you look at recall will be best for this method because it's actually detecting all the edges, right? But if you look at the precision is going to be pretty bad because it's predicting like these 3 and these 3, 6 extra edges, which were not there in the ground truth. All right, so that gives you a sense of what precision and recall means when you perform edge detection. Now, what you do is you have that recall, you have that precision, and you vary your threshold, which is like kind of saying this is an edge or not. So you will have that threshold. So if you vary that, then eventually like you can get this kind of curve. And the idea here is if you have like a very high threshold, which means you are predicting very few edges. So recall is 0. In that case, I mean, if you're predicting few, of course, your precision should be high, right? Because if let's say you're not predicting anything, it's 0, then your precision is kind of, you can say like perfect. You are never wrong. Okay, so that's why the curve starts from the top here. And then as you lower the threshold, which means that you are trying to predict more edges, so some of them will be wrong, then your precision will fall. But since you're collecting more edges, your recall is going to improve. And eventually, if you say like, you say the whole image is an edge, then your recall will be perfect, 100%. But then your precision will go down because most of them will be wrong. Okay, so that's how this curve is plotted. And these are like methods. Some of these algorithms we are going to discuss. The green dot over here, that's like human level performance. And these are various algorithms. We are going to start with Privet and Sobel, which are right here. You can see like around 68 and 70, right? 1968, so 30, 40 years back. And you might say that, okay, this is like, we will study later, like almost a similar kind of algorithm, but with a gap of 2 years. So for today, that seems weird, but if you think about like how it worked, used to be worked like back then, we didn't have internet, anything, right? So you perform some research, then you had to mail like that paper. Even printing was not possible. Sometimes it's like handwritten notes. So just communicating your research was like a year-long process, even more than that. So it might happen that both the researchers were not aware of like each other's work. But today it's like you did something, you just publish online, it's out there, right, immediately. So it's quite different, which is actually good.